I was just thinking about going over the practice exam, just going through each of these problems. I have no idea how many people are going to show up. Um, I can also go over problems, like specific problems, um, that anybody asks, if you're here, right? Because I'll also be recording this. Um, so it could be helpful, right? If you have just one question, then I can get it out of the way. Then you can go, and then I'll record the rest of it, or whatever else I get through, and then you can go view that later. Someone said, can you go over the last question of the practice midterm, the one about isomers? This one? Question 15? First midterm, okay. So question 15 says, draw in bond line formula. So I thought it was line and angle, but we are drawing carbon chains like this, so not with Lewis structures. The linear unbranched isomers that have the molecular formula C5H10Br2 and do not include stereoisomers. How many total isomers are there? So I'm assuming what they mean by linear is just you have a straight carbon chain like that. Let me also pull up the answer key on my end so we can view both. But I'm assuming by this, what they mean is by unbranched is that no carbons are branching off. So you don't have any methyl groups hanging off. So you don't have to worry about any other of like carbon chain kind of isomers. Yeah, this is correct. Otherwise, you'd have way too many isomers to worry about. I will post a recording. Yeah, I will post it tonight. I just have to render it, and then YouTube has to post-process it, so it'll probably be up by tomorrow morning at the latest. I'm not sure how long YouTube will take to process it. So going back to this, we have a linear chain, C5H10, and then we have to have the two bromines. So really what you're doing is just sticking bromines in different spots, right? Because they have to be in, we need two bromines in two spots. So one I can think of right now is bromines on each end, like that. So that's one isomer. Let me get my chain back, right? So I have the linear chain of 5. Another one I can think of is if I just move one of the bromines down. So I could have the bromine here. That's another one. If I move it down by one more, I get that. If I move it down by another one, I get this. So you can kind of fix one group and then move the other one around if you have to switch groups around, right, to see how many isomers you have. Another one I can think of is if we keep following this, there's still two more. That's still Br, or there's one more. I can stick bromine on the same carbon like that. So far we have 1, 2, 3, 4, 5. And then I would actually just do this for all of them and then see which ones are the same structure. So if I were to go ahead and once again, draw the chain, except I'm gonna have bromine in the second to last position, and I'll have bromine here, right? So I'll fix this bromine on the right and I'll kind of move this one on the left. Something you wanna make sure that you're not doing is double counting. So I wanna make sure that this structure is not the same as anything else that I've already drawn. Going up, you can see that this bromine is like two, oh, I missed a carbon, didn't I? Yeah, I did. Sorry. There we go. This bromine is on this N carbon, and then there's 3 more carbons before it's connected to another bromine, or another carbon is connected to the bromine. And you can actually see that same pattern up here, right? Where you have bromine connected to this N carbon, and then there's 3 carbons until there's another connection to bromine. So these are actually the same structure. It's just if you kind of flipped it, um, took it and reversed it like 180 degrees, they would look the same. So let's not count this. I am going to, again, just keep the same trend here. I'm going to fix the bromine here. We're going to move the bromine down. This is clearly not the same as anything else because all the other ones have bromines at the end. Again, using the same logic, I'm going to put the bromine here, just moving it one up one position, I mean. And then that's another one that we haven't seen. I can stick the two bromines on the same one, like that. And then I can also move the bromine at the end, like this, but this is something that we already saw, right? It's the same as this one over here. So make sure you don't double count. Um, then you can have the bromine in the middle, right? So if I take this, if I fix this bromine in the middle, I will once again just kind of move one down, move this one on the left down. This one is something we already saw, or we should have. Did I count this correctly? 1, 2, 3, 4, 5. Yeah. It is going to be the same as this one over here, this isomer, just again flipped. So I'm not going to count this one. The carbon chain again. I have this one. This is not one I have seen yet. So actually, it might be. It is. It's that one. So I have already seen this one. I'm going to do it again, move it down, right? The bromine, two bromines on the center carbon. This one I have not seen yet. If you move the bromine down, you're going to get the same as this and this, right? Because of the symmetry. So you count these all up, and we have 1, 2, 3, 4, 5, 6, 7, oops, 8, 9. And 9 is the correct answer on the answer key. It's not on here, but the answer is 9 isomers. So for all the isomers, the carbon chain should be 5 carbons long. Yes. When should you change the carbon chain? It depends on the question. So in this question, they say that there's no branching. So it says that we have unbranched isomers. So we know that we only have to worry about a straight carbon chain. If they just say isomer in general, I would assume more carbon chains or branching carbon chains. Is there any way of making that take less time, or is the only way we have to is just draw them all out? I think the fastest way is to just draw them all out for most people. Like if I were to look at this, I would know by moving down certain bromines, I'm going to get the same thing by symmetry. So like when I didn't draw the last ones here, you can kind of, as you move stuff down, you can say, I'm going to get the same thing as I did before. But the fastest way is to just draw them all out, right? Because even with drawing them all out, I only had 4 repeats, and those didn't take too long. Any other questions that anyone wants me to specifically go over? Question 13. All right. So question 13, it says in the study of a gas phase decomposition of hydrogen peroxide at 400 degrees Celsius of that reaction, the concentration of H2O2 was followed as a function of time. It was found that a graph of 1 over H2O2 versus time in seconds gave a straight line with a slope of 0.988 inverse molar inverse seconds and a y-intercept of 5.43 inverse molar. Determine the rate law and the integrated rate law expression for this reaction. So for A, how do you tell whether this is really what this is it first order, zeroth order, sorry. Is it zeroth order? Is it first order or is it second order? First, second, third, man, I just said 0, first and second. I'm sorry, guys. zeroth, first, second. You start at 0. All right. So the way you figure it out is based on what they give you. So there's different ways you could figure this out. Sometimes they will give you like a data table. I think there's something in here with a data table, something like this, where you can figure out the rate law. Um, Sometimes they will, like in this case. What they do tell you is that they say that there is a graph of 1 over H2O2 or hydrogen peroxide versus time that gives you a straight line. 12 on the 2021 spring exam. Sure. I'll do that after. So something you want to keep in mind is the plots of each of these. When you're doing for a 0th order, and I'll draw these out. For a 0th order, when you plot concentration versus time, you get a linear line. Keyword linear. For a, did I say first order? I'm going to say zeros. For a first order, when you plot the ln of concentration versus time, then you get a linear line. I think this one goes, was it up? I can't remember the trends. You get some sort of line. As ln concentration of A goes down, I think it's positive. The important thing is that it's a line that you get. And then for second order, for first order, it's negative. Thank you. So then it must be for second order that's positive. So for first order, it goes down. For second order, when you plot 1 over the concentration versus time, you also get a line. So the key word here is a line. Right? Which plot do you get a straight line with? So this is actually the same thing with your post lab this week. With your post lab this week, you're going to plot all of these, and then you're going to see which one of these plots gives me a straight line. And that's how you determine whether it's 0th, first, or second order. So in this question, they're telling you that 1 over the concentration gives you the straight line. Because it's 1 over the concentration, this is going to be second order for the rate law. And then the second part is, do you remember the integrated rate law? Is that on your formula sheet? Does anyone know? I haven't checked it if you have one. But this is your second order rate law. If it's not on your formula sheet, it's just something you're going to have to memorize. Or you could derive it, but I don't think most people want to do that. So yeah. So that's it for A. Any questions on it? How did I do that with the table? Like I said a second ago. So with the table, if they give you data with different things, so like let's say if it was, we didn't have this column, let's say it was just dependent on the concentration of one thing, then you could see whether or not when you double the concentration, what happens to the rate. So if the rate quadruples, you know it's second order. If the rate stays the same, then you know it's first order for like, let's say a half-life or something. But you can plug different values in to see how it changes. So first order, if you double the concentration for first order, then the rate would double, should double. Second order would quadruple, and then 0th order, the rate would stay the same. Do this one quickly. This one's a little bit longer because there's different coefficients. And then someone asked me to do the spring, so I can do it after I do the spring one, after number 13, since 13 is in multiple parts. If a question pops up like this on the test, do we put down both? For which one? 1 or 13? Oh, like if I think it won't be ambiguous. It should just be, oh, they should just give you one thing. It's probably going to be in terms of just one thing. So I don't think you'll have to put down both. Going on to B, it says determine the half-life for this reaction. Seconds. So this one, you just have to remember your half-life formula. They do give you K, right? K, oh, they actually don't give you K. Great. So we actually get to look at the integrated rate law. So if you want to determine the half-life for a second order, I believe it's 1 over K times the concentration. Let me just double check. That's correct. So once you have this formula, right, you need K. You also need the initial concentration to determine the half-life. And then what we can do is plug in, right, for at least A naught. So they do tell you, well, they don't tell you what the initial concentration is. So then let's break this up. They tell you that the y-intercept is this. They tell you that the slope is 0.988. Well, how do you do this question? Remember, the graph that they're giving you kind of by words is 1 over A, 1 over the concentration of A versus time. So if you're looking at this equation here, this is the equation of the line that you're looking at, right? Think of this as y equals mx plus b. So if I was to rearrange it to be exactly mx plus b, right? This would be y is equal to k is your m, because t is your independent variable. Actually, yeah, 1 over a naught or a k. So k is your slope. And then 1 over a naught is your intercept. Now, why does this help? Right? Because they give you what the slope is. They tell you the slope is this, right? Well, you know your slope is k from this equation. This is k. Then they also tell you what the y-intercept is. So they're saying that this over here is b. This is your y-intercept from y equals mx plus b. So 1 over a naught is 5.43 inverse molar. Another way you can write this half-life, because now we have 1 over a naught, right? We don't have a naught. You can write it as 1 over k times 1 over a naught. And now this makes it pretty clear what you have to plug in. So 1 over k, k we said is 0.988. The y-intercept is 5.43. Oops. 5.43. Like that. And then you plug this into your calculator and you get the answer, which is 5.5 seconds. K 0.988. Yes, right here. It's 1 over K.
Wait, I'm confused because in lecture he did it differently. So he divided 1 by 5.43 and then got 0.184 and then plugged that in for A and then multiplied the 0.184 by 0.988.
And he used the exact same equation.
Yeah, but he said that to find A, he put the 5.43 under 1 and then got 0.184 and then he multiplied that by the 0.988.
So he did 1 over 5. So he did 1 over 5.43 times 0.988.
Uh-huh.
Um, if,
No.
or
Oh, well, I guess yeah.
or this 1.43 times 0.988, or this. Oops.
That. And then all of that. under one.
So he did one. Okay, okay. I think I see.
So he
So
first did the
so he
one,
did so he did one over oops, 1 over 5.43 and then times
got a number.
0.988. And then he did one over that.
Yeah, that's what he did. Yeah.
I guess it's tech is technically the same if you take the complex fraction. I think that's a very odd way to do it because this interpretation is directly from your numbers. But if you got the same number, I um yeah, why I get it. So you do get the same number. So I didn't want a complex fraction. He instead said 1 over a naught is this, right? Then what you can do is say, well, I know that a naught is 1 over 5.43. And then he plugged that in to over here. So you got 1 over 0.988 times 1 over 5.43. It is mathematically equivalent. It's a little bit odd, but I guess that makes it more streamlined if you don't want to break the fraction apart. Any other questions? So I see
Okay,
someone said,
thanks.
if it was first order, would the thing that gives you a straight line be ln of something? Yes, that's correct. Okay, going on to C, it says how much time is required for the reaction to be 85% complete in seconds. So when a reaction is 85% complete, that means that 85% of the initial concentration is gone, right? That's a way you can think about it. I'm going to say that this time elapsed is at time TE. You can notate it however you want. I'm just going to say TE for end time. Subscripts are just labels. So that way, again, going back to the integrated rate law, I want to make it very clear that the concentration is a function of time. Right? I said this in discussion multiple times. It is a function of time. It helps you solve these. So I would recommend thinking about it like that. 1 over a naught. Then what we can do is say, okay, well, at some time where this is ending, right, where I'm measuring this, where it's 85% complete, I have K, this is TE, so however long it takes, right? Plus 1 over a naught. Well, that didn't really do anything. I have this equation and I have a lot of unknowns that I can't do anything with. I have K, right? And I have 1 over a naught, but I have TE as an unknown and concentration of A as an unknown. However, what you can do is say, at this time, I know how much reactant I have left, right? Because at this time, I know that 85% of this reaction is complete, or that I have 15% of the original concentration, right? No, I converted, it's 0.15, so converted from percent to a decimal, right? But if I'm 85% done, I have 0.15 of whatever I started with, or times whatever I started with. If I was 50% complete, I'd have 0.5 of whatever I started with, 0.5 times whatever I started with. So now you can go ahead and you can look at this as a system of equations. You have an unknown here, right? You want to get rid of this concentration. You don't care about it. You want to solve for the time. So if you plug that in, you get 1 over 0.15 times a naught is equal to K, which we have, versus the time that this is taking. 1 over a naught. And now you can solve for TE, right, just by algebra. Um, so if I go ahead and I subtract 1 over A naught from both sides. I get this. And then I go ahead and divide by K. If this gives me the time, and then you can plug in all of your values. The reason I'm writing this generally and not plugging in numbers is because I saw somewhere else on the midterm, I read who asked me about it. I think there's a few people that asked me, but there's a problem that you do not have the initial concentration and you cannot solve for it. And what happens is when you plug, I think you solve for K first, and then when you plug it into the equation, the initial concentration ends up canceling out entirely. So again, I recommend keeping everything general until the very end in case things do cancel out or in case you can't find things, right? Then so that way you don't get stuck. So when you plug all of this in, this is 1 over 0.15, and then I guess you could plug in the fraction, right, from above. So what Professor Longacre did. So A naught is 1 over 5.43. 0.543 minus 1 over 0.543 divided by K, which is 0.988. And then apparently you get 31.2 seconds when you plug this in. Any other questions on this? So someone asked me before, so the order right now is hopping over to 12 on spring 2021, and then the first one in this test. Any other questions on number 13 here? Oh, okay, great. So then we won't go to 12 since it's similar to this one. Thank you for letting me know. So then we can hop back to this one over here. So it says determine the sum of the orders for NO and O3 based on the data below. So this is the one, I think it was like on page 2 on the kinetics worksheet that we did in class, where you can write they want you to find the orders of each of these. Basically, you're going to write the rate law, and you can't assume anything about the exponents. So I'm going to say that NO, the first reactant, is to some power A. You can use XYZ if you want. Do whatever. And the reactant B is to some power B. If it's 0th order, right, you will be able to mathematically solve for it being 0, right, A or B. If it's first order, you'll get 1, second order, you'll get 2, maybe even third or something weird. You'll get that number when you solve for it. What you do here to solve for these is you use this, the first rate divided by the second rate. So the rates that you have over here is what we're going to plug in for the math is equal to K. And then this is of the first rate or the first whatever experiment it's denoted with. So I'll write it like this. We'll put a 1 down here. B1 on the bottom. It's the same thing. It's just with whatever that second one is. Where the subscripts are indicating one reaction, right? One experiment of data. The reason you divide these is because, again, you have a system of equations. So this is how we solve it. You want to find A and B. You have a whole bunch of unknowns and things that you measure, and you have K. And the only way to make K go away is to divide these equations. So when we do this, the K's are the same. They go away. Now what we can do is if you want to solve for A, yeah, let me move this over. If you want to solve for A, what you have to do is look at 2 experiments where O3 is kept constant. That way, the terms with B cancel out because it's going to be the same on the top and the bottom when you divide. So if I solve for A here, I'm going to use experiments 1 and 3 because the O3 concentration is kept constant, and you're going to see that the B's are going to go away. They're going to cancel out. So for A, I'm going to plug in the first rate for experiment 1. Doesn't matter whether you put on the top or the bottom. I could put 3 on top, the other on the bottom. But this is 0.257. For the third one, it's 0.515. The K's went away, so I won't write those in. The concentration of NO in the first one is 0.0784. That's to the A power. For O3, it's 0.0325. That's to the B power. On the bottom, the concentration of NO is 0.157. That is to the A power. The O3 is the same. And you'll notice, right, as we chose the experiments correctly, these are the same, right? And because they're the same, when you divide something by itself, you get 1. So then it just becomes this equation here, right? You're left with 0.257 divided by 515 is equal to that. You plug this into your calculator, this is about equal to 1/2. And then this is going to be, so I'll actually plug it in to give you the actual numbers. 257.515. 0.499. It's 0.5 to 3 decimals. Then on the right side, it's going to be about the same. Should be about 0.5. 0.07. Yeah. This is 0.5 to the 8 power. Now you have to solve the equation, right? 0.5 to what power, or the 1 power, is equal to 0.5 to the A power. Here, A is clearly equal to 1, right? Can't be anything else because the base is the same. You could take the ln of both sides. You could use logarithms. They have the same base, so you can just set the exponents equal to each other. So A is equal to 1 here. You can do the same for B, right? So for B, you would go ahead and keep NO constant. So we're doing the exact same thing, just the other way around. For B, we have trials 1 and 2, or experiments 1 and 2. So with the first rate, we have 0.257 divided by 0.515 for the rate. Then for NO, we have 0.0784. This is the same on the top and the bottom, right, by choice. So that way the A's cancel out. You could plug in the A right now if you wanted. You could actually, since there's only 2 things, you could even plug in A and then just algebraically solve for B, if you know how to use your logarithms. But I will keep doing it the same way for consistency. This is 0.0325 to the B. Sorry that my running out of space here. Writing is getting a little bit messy. And then we have 0.065 to the B on the bottom. You go ahead, you cancel this out. This turns into 1, right? On the left, this is equal to 0.5. On the right, it's also about, should be 0.5 to the B power. And then you get B is equal to 1. You add up A and B. It's asking for the sum of the orders. So with respect to NO, this is first order. With respect to O3, it's first order. You add them up, 1 plus 1, right? You're just adding up the exponents is what it is, and you get 2. Any questions on this? Let me check the chat now. So I don't see any other questions for this problem. Someone asked if I can do 5 and 6 on the fall one, on this one. I can. So going on to number 5, it says, what is the hybridization of the atom indicated by the arrow? So when you're checking hybridization, what you want to do is, or an easy way to do it, is check how many pi bonds that atom has. If you have something that is sp3 hybridized, this is not always true if you take OChem, but it's true for this class from discussion worksheet answers. If it is sp3 hybridized, you have no pi bonds. If it's sp2 hybridized, the atom has 1 pi bond. I don't know why I wrote bind. If it's sp hybridized, it has 2 pi bonds. And I don't know anything S hybridized with 3 pi bonds. So you don't have to worry about that. But this is an easy way to do it. So if you look at this atom, another way you could draw this out is like this. Carbon, hydrogen, hydrogen, and hydrogen. You can see here that this carbon has 4 bonds, 4 single bonds. There's no pi bonds, right? There's no double bonds. There's no triple bonds. So this one is going to be sp3 hybridized. And then that's it for this one. Any questions on this? And then I'll go over number 6. Someone asked, is the rate law equation on the sheet, or do we need to memorize? I don't know. I don't. Does he post the equation sheet? Someone says it's on the sheet. Thank you. So I guess you don't need to memorize it. You may need to know which one is 0th, first, and second order. Oh, it tells you. Oh, wow. Okay. Easy then. So it's all on there. What it sounds like. Okay, so I don't see any other questions on 5, and then is asked to do number 6. So number 6 says, what is the hybridization of the atom indicated by the arrow? So we can do the same thing here, right? Just using the same trick. Looking at this atom, this carbon, there's 4 bonds for carbon. There's this single bond, and then there's this triple bond. In the triple bond, you have 2 pi bonds. So the hybridization here is going to be sp. Then you're done. You can count the number of things. So an equivalent way to do this is how many atoms is it attached to? The reason it's easy to make a mistake doing that is you miscount. So if you have 4 things attached or 0 pi bonds, 4 electron groups on a carbon and 0 pi bonds, that's sp3 hybridized. However, oftentimes people will forget there's hydrogens and we'll be like, oh, there's 2 things, right? So this is sp hybridized, and that's not true. So I recommend going based off of pi bonds for hybridization. You can count number of electron groups. That's technically okay. That is okay to do, but just be careful. Someone asked if I can do number 10, 8, and 10. So going on to number 8, it says, how many pi bonds are in the following molecule? So looking here, pi bonds are again the second bond that gets made with second or third bond that gets made between 2 atoms. So here we have a pi bond, right? There's a carbon that's double bonded to an oxygen. That first bond is a sigma bond. The second bond is a pi bond. So there's 1 pi bond here, 1 here. So 1, 2, 3, 4, 5. So we have 5 pi bonds counting it up. Did I miscount? No, I didn't. And then that is your answer. Any questions on this one? Okay. So I'll go on to number 10. And why they're called pi bonds is another topic in itself. It has to do with orbital alignment. Um, Pi bonds are made with p orbitals. Sigma bonds are made with hybridized orbitals. I'm not sure if that was something that was covered in class. And 9. Okay, yeah, I'll do 10 and then I'll do 9. It says how many lone pairs are in the following molecule? So here is where remembering some stuff in 2A would be helpful. So in 2A, I think it was in 2A, maybe it was 2B, but you covered formal charge at some point in your chemistry career. Um, when something has a 0 formal charge, it's usually the most stable state for that. In organic chemistry, this is pretty much always true, almost always true. Things with 0 formal charge are generally much more stable than things with formal charge. So how do you figure out formal charge on things? There's an easy way looking at the periodic table. I don't have one on me or downloaded here, but if you look at the periodic table, on the right side, so on the where the halogens are, skip the noble gases because you're not going to see them bonded to stuff and OChem. At the halogens, so the second to last column or second to last group, all of those halogens want to be bonded with one thing. They are one electron away from a full octet. They're one group away from a full octet. They want one bond. So if halogens have one bond, they have a neutral formal charge. Okay. If you add a bond, it goes to a positive formal charge. If you subtract it, it goes down. That's a much easier way to do it than do the whole calculation shenanigans that you had to do, like number of lone pairs, number of valence electrons. I don't even remember it. But this is a much easier way. So halogens want one bond. You add another bond. So if the halogen is double bonded, it has a positive formal charge. If you go down a bond, so it has no bonds, right? It's an ion. It has a negative formal charge, which is true, right? Cl minus as an example. You go to the next column, that's where you see oxygen. This is not really true for sulfur, but it's true for oxygen. Oxygen wants two bonds, right? And there's a reason I am saying this. It does relate to this for lone pairs. Oxygen wants two bonds and two lone pairs, while halogens want one bond and three lone pairs. In organic chemistry, we again work with 0 formal charge the vast majority of the time when we're writing stuff out like this. Go one over, you have nitrogen. Nitrogen wants 3 bonds and 1 lone pair. So if you're looking at all of these, you can fill in the lone pairs for oxygen. Oxygen has 2 bonds. Assume it has a full octet. 2 bonds and it has 2 lone pairs. Same thing here. Nitrogen has 3 bonds. It's going to want that 1 lone pair. Same thing over here. And then you can just count them up. So you can do this based off of formal charge. I'm not sure if they'd have you do anything wacky with it, which is why I kind of went more into it. But you need to fill up the octets for each of these. The easy way to know is how many bonds do they typically have, which is 1, 2, and 3. And then you just fill in the lone pairs to get the full octet. And then you go ahead and count them up. So we have 1, 2, 3, 4, 5, 6. And that is your answer. Any other questions on number 10? I don't see any. And again, the reason why we fill up the octets has to do with minimizing formal charge on the molecule. So I'll do number 9 and then number 11. So number 9, it says a reaction is 50% complete in 45 minutes. How long after its start will the reaction be 93.875 complete if the reaction is second order? So I'm going to do this in a very similar way as to how I did 13. When a reaction is 50% complete, that means the half-life or half of the reaction is done in 45 minutes, right? Both of these things together are telling me what the half-life is. They're telling me that the half-life is 40 minutes because it takes 50 or 45 minutes for half of this thing to finish. Okay. So if they tell you it's 75%, then that's not the half-life, right? But 50% means it's the half-life, and then they just give me the value. Why is this important? And now this was the question that I was actually saying that you cannot cancel certain things out sometimes. So I always solve for things generally. So the half-life for a second order is this, as we just did a second ago, right, from 13. Now, what we can do is it says, how long after its start will the reaction be 93.875% complete after the reaction is second order? So once again, I'm going to use the same notation. How long after its start? I'm going to say this is at some time, TE. Right? You can use whatever you want. 45 minutes. Oh, thank you. Yes, that is correct. I wrote 40. It's supposed to be 45. Thank you. I'm going to use TE for the time elapsed for this 93.875 to be done. Right. Now I am going to write the integrated rate law. I'm going to write the general form first, so we're all on the same page. So that's what it is. Now, the second part from what they're telling me that it's 93.875% complete. They're telling me at this time, however much time has elapsed, I'm going to have 100% minus this percent left of my original amount. So before, what was it? Before it was 85%. So I had 15% left, right? Here I have some number, such a long decimal, 93875. Oops, 875. We have 6.125% left. So we can say after this elapsed time, I have 6% of my original concentration, right? I just change it to a decimal from a percent because you don't multiply percents with stuff. Then I can go ahead and plug these in. So I'm going to do this. 1 over A at some time that is being elapsed is equal to K, which I will substitute in a second, times this time elapsed, plus 1 over the initial concentration. We can keep in mind that, and I'm actually just going to use the transitive property here. Let's just make this easy. We can keep in mind on the left side here, A, the concentration of A after this time is 0.06125 times the initial, right? From what we got over here. Then you can solve for TE. Now the problem is that I don't have A, not. I don't have TE, right? That's what I want. I want TE. And I don't have K, right? What you can do here is solve for K in the half-life. They do tell us the half-life is 45 minutes. And we can solve for K. Why would I do that? Because I don't have the initial concentration. You'll see. So I do have the half-life up here, right? And I can use this to solve for K. I get K is equal to 1. Let me move this. K is equal to 1 over 45 times the initial concentration. I just want to get rid of it in this equation, which is why I want to substitute it, right? The reason I waited on solving for K is it's not really clear which thing you want to solve for. right? Would you solve for A naught or would you solve for K? You can actually solve for either and it will cancel out. K is going to be easier here though. Then when I plug it in down here, 0.6125 times A naught, that's equal to K, which is 1 over 45 times A naught times this time elapsed plus 1 over A naught. You'll notice that everything has an A naught or the initial concentration in the denominator. So what you can do to get rid of that is if you multiply both sides by the initial concentration, right, multiplying everything by A naught, everything goes away. Then you're left with an equation that is just algebra. 0.06125 is equal to 1 over 45 times this time elapsed plus 1. And you can just solve for this time elapsed by algebra. So to solve for this, I subtract 1 from both sides. So I get 1 over 0.06125 minus 1. And then I multiply by 45 to isolate the TE. You plug this into your calculator, and then you get, I forget, 360 minutes. And then that is your answer. So,
Wait, he said it's supposed to be 689.
or is it 689 when it's plugged in? Let me plug
Yeah,
it.
it's when it's
Yeah.
plugged in, it becomes 689.
Okay, thank you. So then this is not correct. Oh, thank you, thank you. This is 689. Okay, thank you. Great. Any other questions on this? Thank you guys for plugging that in. I assume the answer key was right. Oh, wait, the choices are different from the key. Weird. Yeah, weird. Okay, I'll let them know. Okay. So next was I was asked to do number 11. So let's do that. It says calculate the activation energy in kilojoules per mole for a reaction that takes place at 500 Kelvin with a rate constant of 2.42. So that's K. And the same reaction that takes place at 700 Kelvin with a rate constant of that. So immediately, when you see activation energy, you're going to use one of two equations. You're going to use the Arrhenius equation, right, to calculate K. That's one of them, right? I think it's K is equal to A E, was it? I think it's negative EA over RT, right? That's one. Yes. I'm not sure if there's a negative up there. I'm pretty sure it is. It's a probability. The other one is this. K1 over it's K2. That's how they notate it. K2 over K1 is equal to EA over RT. No. And then it's 1 over T2 minus 1 over T1. I believe that's both of them. The way this one gets derived is dividing two of these top equations with different Ks. But when you see activation energy, you're going to use one of these formulas, right? Because they're the only two formulas with activation energy. So which one do you use? You look at the data, you look at what you're given, right? So they tell you that you have two rate constants. They don't tell you anything about a capital A, right? Or a prefactor. Since you have two rate constants, you're going to use the equation with two rate constants. So we're going to use the second one. I'm going to go ahead and erase this first. Okay. And then this actually just ends up being plug and chug and solving algebraically. So once you know this, this is the equation you're going to use. I plug in both my K's. So it says I have one with a rate of 2.42 times 10 to the negative third. If you're wondering, well, that's the first one they give you, right? Don't you have to plug that in on the bottom? It doesn't matter as long as you keep it consistent. So if you plug in whatever you plug in on the top of the fraction here, make sure you plug it in on the right of the subtraction sign over here. It'll all work out math-wise. 2.42 times 10 to the negative third, that's the first one. The second one is 6.70 times 10 to the negative third. The activation energy is what we want. R is your energetic constant of 8.314. This is in joules per mole Kelvin. I won't write in the units. Actually, I do want to make a note of it though. Really key thing is that this is in joules. Please keep that in mind. That's the important part. So that's 8.314. 1 over T2. So the temperature that corresponds to this bottom one, 700. 700 minus 1 over 500. And then you just algebraically solve for EA. So yeah, I would write this. I would multiply both sides by 8.314 and then divide by this. So I would get EA is equal to ln of 2.42 times 10 to the negative third, 6.70 times 10 to the negative third. I'm multiplying both sides by 8.314. Then divided by 1 over 700 minus 1 over 500, right? Because one term is dividing EA. Isn't it switch 2.42 as K2? Oh, thank you. Whoops. Yes. Yes. Thank you. Good catch. So I did not keep that consistent. Thank you. Thank you. That should be 500 and 700. I swapped the two. 500, 700. T2 goes first. Yes. Thank you again. And then you can plug this into your calculator. I always recommend plugging in everything at the end in one big fraction. Your calculator, most calculators now should have a fraction, especially if you're using a graphical calculator. So like the TI-84, you hit alpha and then the one next to it, you can get a fraction, the one to the right of it. If you have a TI-36X Pro, that's a very nice calculator. I think it's like 20 bucks. I recommend it. You can also plug in everything in one step with the fractions. And just make sure that you don't have any rounding errors, and also make sure that you don't, what was it? No rounding errors, that you're not doing anything funky with the parentheses and messing up. I've seen that happen a lot. And it's easier to just double check that you plugged in everything correctly. So I always recommend doing it in one step because calculator errors happen all the time. So then when we plug this in, we get negative 14,816. And this is in joules per mole, right? Because R has units of joules. Your EA in both equations, in both the one with the prefactor A and in this one, will have units of joules. So keep that in mind. If you have like a free response question and you have to find activation energy, both equations use EA in joules. So if you're given the activation energy in kilojoules, make sure you convert to joules. And then the answer here, I got a negative, but it says it's positive. Is there a negative up here in the formula? Looks like something got dropped. So it is 14.8 in terms of magnitude. Let me check your equation sheet. But do make sure you convert. Is the equation sheet on Canvas? Practice exams, discussion worksheets. Oh, it's through equitable access. Oh, no wonder I haven't seen it. I did not check there. Oh, there's also probably one in the very back here. Forgot about that. Let's see. Did I drop T2 minus T1? Oh, so then I swapped something here. K2 goes first. That's weird. I could have sworn I saw it written differently on a different answer key. So this is actually swapped. T1, T2 by the equation sheet. So then these are actually back swapped. My apologies. And then all that does is change the sign to a positive. So this is in joules. You convert this to kilojoules, and you get a positive 14.8 kilojoules per mole. Any questions on this one? Yeah, take the equation, make sure you use the right one. Don't be like me. And then plug in and then solve algebraically. Do make note of the units, though, of activation energy. It is in joules, not in kilojoules, in both formulas.
Wait, on the equation sheet, it says it is T2 minus T1.
And they do T2 minus T1, but I think they swap the two Ks. So then would it be something, so the equation sheet would be like this, right? Is it that?
Yeah.
Yeah. So then they just change the indices. This will still be the same. Any other questions? Okay. I see. Okay, someone asked if I could do number 4. So we'll go to that. It says identify the 3 functional groups in the following molecule. So oftentimes there's an alkane functional group, which is not in the answer choices. So I guess we're ignoring that. Functional groups have different properties in organic chemistry. So the parts that look different are usually parts that are a functional group, or the parts that have something kind of that is not carbon, right? A carbon-carbon bond. Those are usually the ones of interest. So we have a functional group over here. This is a carbonyl functional group, C double bond O. There's a whole bunch of them that you'll have to know. Which one is it? It depends what the carbon is connected to. So we'll talk about that. There's this nitrogen connected to a carbon. That's one. You have another carbonyl functional group here. So the functional groups here, knock out the easy one. If you have a nitrogen bonded to a carbon that does not have a double bond to oxygen, this is what we call the amine functional group. So it's a carbon-nitrogen bond without this C double bond O anywhere, or on that same carbon, I should say. So that's an amine. Up here, we have this carbonyl. What dictates what kind of functional group the carbonyl is this thing that hangs off, right? If it's 2 carbon chains, it's a ketone. If it's a carbon, or if it's an OH group like we have here, this is what we call a carboxylic acid. If it's an oxygen with a carbon group, that would be an ester. If it's a carbon with a nitrogen, like the one down here, so carbon double bond to oxygen with a nitrogen hanging off, this is what we call an amide. If you see something weird and symmetric, I don't think you guys learned acid and hydrides, but that's another one. I think that's it. Yeah, I can't think of any other carbonyl functional groups. There's also acid chlorides, I guess, but I don't think you have to know either of those. So once you know all your functional groups, it is just kind of a thing you have to memorize and then recognize it in the molecule. So we have the amine, we have N single bond carbon with no double bonds to oxygen. We have that carboxylic acid on the top, C double bond O with the OH. Then we also have C double bond O with the nitrogen, which is the amide. So this is amine, amide, and a carboxylic acid. There is actually one more carbonyl. It's the aldehyde. It's where it's a hydrogen on the carbon. Okay. Any other questions on this? I'm going to do number 15 next on a different exam. Okay. So give me, oops. 1 second. Let me go ahead and download that. Files. I haven't. Oh, that's okay. Okay. I haven't taken a look at this one yet, but I assume it's going to be something similar. Sorry if I'm a little bit slower on this one. Folder. Recorder. Let me share my screen again. And it was number 15. So number 15. It says, it's part 2, short answer. It says, write the most plausible Lewis structure for the following. Write the P2 fragment with a 0 formal charge that could form molecular phosphorus P4 based on the following chemical reaction. Okay.
We were told
Yeah.
that this isn't going to be on our exam.
Oh, great.
Okay, that's lovely. Thank you.
Okay, cool. Okay. Any other questions? From this exam, from another? Yeah, that's really weird. I'm looking at the answer key and it's radicals. Hmm. Could I go over drawing structural isomers and cyclic isomers? Is there a specific question on one of the tests? So I finished number 15, and I will be uploading the recording, and so you can check that for number 15, where we draw some structural isomers with the bromine. I don't think we saw anything with a cyclic isomer though. Is there anything in here? Oh, well, okay. We knew this one. It says draw in bond line formula the 12 cyclic isomers that have a molecular formula of C6H12. So something that I did with the linear chain, I'm not sure if you were here for that one, but for the linear chain, I drew the base chain and then I kind of just moved I fixed one group and I moved the other things around if I could, if there was anything. I'm going to be doing the same thing here, a similar idea. So we have to have a cyclic isomer, which means that it has to have a ring, right? We draw 2 rings. No, I guess not. Yeah. It's 1 degree of unsat. So we're going to draw things with one ring in it. Yeah, so there's different types of rings you could have here with 6 carbons. You can have a 3-membered ring, which is a triangle. You can have a 4-membered ring, which is a a box, sorry, a square. You have a 5-membered ring, which is a pentagon. You can have a 6-membered ring, which is hexagon, and that's all we can go to, right? Because you can't have a 7-membered ring with 6 carbons. You can't have a 2-membered ring. So in each of these, right, you can keep count of how many carbons you have left. In a 6-membered ring, I have no carbons left. In a 5-membered ring, I have 1 carbon left that I can move around, that I have to put somewhere and do whatever. In a 4-membered ring, I have 2 carbons left. And then in a 3-membered ring, I have 3 carbons left that I can move around and do whatever with. So let's start with the easiest one, the 6-membered ring. There's only one way to draw the 6-membered ring, which is the 6-membered ring itself, right? Because I have no leftover carbons. So that's done. That's one isomer. For the pentagon, I first draw the ring, and then I put a carbon on one of these carbons, right? I put a methyl group. So now I have 6 carbons. I have my 12 hydrogens. Now, no matter where I put this methyl group, I'm going to get the same molecule, right? Because I could always rotate it, right? Like this is the same as this, which is the same as this. Oops. Which is the same as this, right? And so there's actually only one isomer for the cyclopentane or methyl cyclopentane. Moving on to the 4-membered ring, I have 2 carbons left. Right, we have 12 isomers to account for, so should be quite a lot here for the 3 and 4-membered ring. So the 4-membered ring, I'm just going to go ahead and put a methyl group there. Right, one isomer is I put a methyl group across from it. Another isomer is I put the methyl group right next to it. It'd be the same as putting it down here. Another one would be if I put the methyl group on the same carbon, like that. And then that's it. Those are all the isomers. Right, I fix one thing and then I move it around to get all the isomers. I think that's the easiest way. At least that's how I do it. Going on to the 3-membered ring, I'm going to do the same thing. So I have 3 carbons left. There's 2 different types, I guess 3. No. 3, yeah. 3 different types of combinations of groups you can have with 3 carbons. You could have a whole 3-carbon chain, right? You could have a 2-carbon chain, so an ethyl group, and a 1-carbon chain, so a methyl. You could have 3 1-carbon chains, right? That also works. And then we're just going to do a whole combination of all of these. So I'll start with the 3 chain. So if I have these 3 carbons left, I could put them in a chain of 3, like that. Doesn't matter where I put it. These are all going to be equivalent isomers. So that's 1. Now I can also have an ethyl group, or the 2 carbons. I'm just going to go ahead and put it on this one on the corner, and then the methyl group, like that. If I move the methyl group up, so word of warning, these are the same, these 2, right? It's kind of like flipping this one over, pretty much. And then you could flip this one as well because you can rotate around single bonds, but those are the same. Another one is I could have the ethyl and the methyl on the same group like that. This is it for an ethyl and methyl group. The next one is the 3 methyl groups. So I can have them all on different ones. I could have 2 on the same one, like that. And I can't have 3 on the same one because that would violate the octet rule. Oh, I made one mistake because there's different types of propane that you can have, right? Propane, you can have a straight chain. You can also have it branch out in the middle like that. So let's count. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm missing one. Oh, and then for the 4-membered ring, I missed the ethyl group because I had 2 carbons left. My bad. There we go. And that is it for this one. Any questions on this? So you can draw your ring, see how much stuff you have left, right? What kind of groups can you make with the carbons you have left? Can I make ethyl groups, a propane group? What kind of propane groups? Ethyl, there's only one way to draw it, same with methyl. So be careful with the propane. Like I missed it. And then you can just move them around. Okay. I don't see any other questions on this. Nobody has asked any other questions or specific questions on either test. So I guess I might just do a problem. I guess we'll just do 19. Since it's not too long, and if anyone wants me to do a question, you can it won't take too long to get there for me to finish this. So number 19 says answer the following questions based on the reaction diagram below. No partial credit. So A says how many intermediates are there? So intermediates in this are formed at the wells in the middle. Right? They're things that form but go away, but they're stable enough to actually form. Okay. So that's why they're in these wells, these potential energy wells is what they are, right? They're what we often call metastable, but you don't need to know that. So they're in these wells. You have these intermediates. So how many intermediates are there? There's 2. That's it. Next, it says how many transition states are there? This is how many hills there are. So there's 1, 2, 3, right? A transition state is transitioning from one thing to another. So you can think of it as how many times does it transition from one thing to another? So from A to B, that's one transition. That's one hill that you see. From B to C, that's another hill, right? That's another transition state. And then from C to D, that's another. So that is 3 transition states. Going on to C, it says which is the fastest step in the reaction? The fastest step here is going to be the one with the lowest activation energy. That is the fastest step. The activation energy for any of these is from where the energy of the reactant is to where the energy of the transition state is. Right, so for A, that's the first activation energy, or the activation energy from A to B. From B to C, there's that. Oops, did I say, no, yeah, okay, I said lowest, that's correct. From C to D, that's the activation energy. Which one is the shortest, right? For the fastest step, it's from B to C. So the fastest step is from B to C. And that's it. which is the rate determining step. The way you can think about this is slowest. And so slowest is going to be highest activation energy. Which is from A to B, right? The gap is just the biggest. E, it says, is the first step of the reaction exothermic or endothermic? Endothermic is where the products are higher than the reactants. Exo is where the reactants are higher than the products in terms of potential energy. So from A to B, it's going up, right, in energy. So this is endothermic. And is the overall reaction from A to D, well, A is lower than D. So there's an absorption of energy, which means this is also endothermic. Any other questions? Any specific questions? So I don't see anything in the chat. No one is saying anything. Okay. Hope I didn't put everyone to sleep. I guess I'll try to find another one. Let's see. Yeah, we can do this one. So number 18. Do you guys have to know steady state approximation? Does anyone know for your midterm? I know it shows up on the discussion
Yeah,
sheet. Yes, okay.
I think he said that we are gonna get a question like that.
Great. Okay, thank you. There's two steady state approximations. There's one on this test, and I think there's one on the other. Let me see the other one. Let me see which one I like better. I think I like this one better because it's a general. So yeah. Derive the rate law. Oh, I guess they're both the same. Yeah, but let's do this one. The other one's a little bit easier because it's multiple choice. So it says we have this following chemical reaction. The reaction takes place over two steps. Use the steady state approximation to derive an equation for the formation of NOBr. Now, when you're looking at these problems, right, you're looking at the rate of formation for NOBr. Or you want to look at the rate. I think, do they write it as a derivative? I think that's how they write it. The rate of the formation of NOBr is going to be equal to something with the rate of concentration of the reactants. Sorry. Right, so you start with certain things. In this case, you have NO and you have Br2. And I'm going to have some rate of this form. Okay. I want to make that clear that it's going to be of this form, which is why we end up replacing some stuff, right? But we want it in this form. We want something with just nitrogen monoxide and bromine. Why? Because those are the two things that show up in the first step, right? Those are the two things that are going to combine, and there is an intermediate, but they do end up making NOBr. So I want it in terms of that and not anything else. Now it says use the steady state approximation to derive an equation for the formation of NOBr. Well, if I were to just write, so without even considering the steady state yet, if I were to just write the rate of NOBr, right, not NOBr2, NOBr, I would say the rate of formation of NOBr, and this is just rate, right? But it's being specific as to which thing is changing. I can look at the second reaction, right? I would just write my rate law for this. So my rate law, where NOBr actually forms, is the concentration of NOBr2 to the first power, right? Because there's a coefficient of 1. And I forgot a K. This is K3, right, for the formation going forwards, times the concentration of NO to the first power because of the coefficient of 1. I just told you a second ago that I only want this in terms of nitrogen monoxide and Br2, right? Here, I have NOBr2. This does not show up in the rate that I want, right? I want this in terms of the reactants that I start with, not in terms of the rate of the rate limiting step reactants, or the step where it forms, the product that I want forms. So what I want to do is I want to get rid of NOBr2, right? That's really what we want to do. We want to get rid of this thing. I don't want it anymore because it doesn't look like the overall rate law. So how do I do that? What we do is we use a steady state approximation. So what does that mean? The steady state approximation means that as quickly as you're forming something, it's going to disappear just as quickly. Or there's this equilibrium of formation and consumption, right? Which is the definition of equilibrium, equal rates. So what you can do, and I think the way they wrote it on the answer key is, I like the way they write it. I think on the discussion key, I just wrote out the approximation, and I didn't write stuff explicitly, but I'm going to write it out here. So the rate of formation, I'm going to put positive sign like they do in the key, of NOBr2, the thing I want to get rid of, because it doesn't show up in my overall rate law. The rate of formation is positive, right? Please note, that's why I'm putting a positive. This is equal to the first rate law, right? It's just K1, the forwards reaction, so rate constant for the forwards reaction, times the concentration of NO to the first power, times the concentration of Br2. That's how quickly this is forming. Again, this is rate. Oh, he doesn't expect you to put derivatives. Okay. So then I will write the rest of this in terms of less math terms. So I'll say rate of formation. And this is for the concentration of NOBr2. So the rate of formation is that. It's just the first rate law, right? How quickly you're writing it. Rate is equal to K times the concentration of reactants to the powers. Then we have the rate of consumption. Now there's two things you want to consider here. All right. The first one that's obvious is this one, where you consume it to form NOBr, right? It reacts with nitrogen monoxide. So you have this reaction, K3 times the concentration of NOBr2 times NO. This is where it's getting consumed at some rate. However, it's also being consumed in the first reaction, in the backwards reaction, right? The second reaction only goes forwards, but this one can go backwards, where you have NOBr2 decompose into NO and Br2. The rate law for the second one is K2 times NOBr2, right, for the backwards. And both of these together are telling me how quickly it's getting consumed, right? Essentially, how fast is it getting used up in the second one? And how fast is it going backwards in the first one, right? It doesn't like being NOBr2, so it decomposes and goes back. But these are the two ways it's being consumed, right? And the rates that they're being consumed. Now, the steady state approximation, or the pseudo steady state hypothesis, we're saying that the rate of formation is equal to the rate of consumption. That's what the steady state means, right, that you're forming it as quickly as you're consuming it. And what you can do is write this out. K1, right? This is for my rate of formation. K1 times NO times Br2 is equal to K3 times NO Br2 times NO plus K2 times NO Br2. Now, what was the point of all of this? Right? Why would I go through all this trouble? Well, now I have an equation where I can solve for NOBr2, right? I can solve for NOBr2 in terms of Ks and in terms of nitrogen monoxide, NO, and Br2. That means I can take my NOBr2, whatever I solve it to be, and then plug it back in here because I didn't like it. I want to get rid of it, right? It does not look like the overall rate law that I want, right? I want to get rid of NOBr2. So solving for NOBr2 here, now it's just a whole bunch of algebra. I know it doesn't look like it, but it is as it's at its heart, right? You are just pulling things out, factoring things and stuff like that. So I will go slow here. I factor out the NOBr2 from both terms on the right. K3 times NO, and then plus K2. So I just factored it out on the right side because they're multiplying by the same thing, right? Like 2x, y plus 3x. You can factor out the x to get x times 2y plus 3. Then I go ahead and I divide this term out because I want NOBr2, so I can plug it back in because I didn't like it, right? It doesn't look like the rate law I want. And then I get K1 times NO Br2 divided by K3 times NO plus K2 is equal to NOBr2. And now I get to plug this back in. So substituting this in here is what I'm going to do. Right, I'm gonna literally plug that in here. I'm gonna substitute. That gives us that the rate that NOBr is being produced is equal to K3 times NO, so that's from the original, right? That's just these two terms, times this whole thing, right? It's going to, this K3 and NO are going to multiply with the things in the numerator. So this is times K1 times NO times Br2 divided by K3 NO plus K2. You can't cancel these out, right? Because there's a plus on the bottom. And then you can go ahead and simplify this. So simplifying this out, you can bring the NOs together, right? So distributing, so that's NO squared on top. I'm going to move the K's together to make this a little bit nicer. Now I'll move these over. And then that is the answer. K3 times K1 times NO squared times Br2 over K3 times NO plus K2. That is it. So again, you can figure out the logic behind this is you want an overall rate law that looks something like in the terms of your original or your reactants, right? Just the reactants in the first step. You find the step, typically the rate determining step, that determines how quickly the thing that you want, the formation of what you want, is forming. So the rate law for this is the second one, right? That's where the NOBr is forming. Then you say, well, that's not in terms of the original reactants. I want to substitute one of these. Then you use the pseudo steady state hypothesis to do the substitution is what all of this is, right? You substitute it and then you plug it in. So any questions on the first part before I go on to the second part? Okay, I don't see any. All right, moving on. B says derive a rate law to produce NOBR if K2 is significantly less, or sorry, greater than K3 in the second step. So you're still using this thing. We didn't do all this for nothing. So once you get this, this is still going to be used. I'll just rewrite it. This is rate is equal to K3 times K1 NO squared BR2 K3 A3 NO plus K2. That's it. Now it says K2 is significantly greater than K3. What this tells you is when you have a sum or subtraction, you can, let's say, of K3 and K2, you can ignore the K3 term. What this is saying is that K2 is so much bigger than K3, it does not matter whatever K3 is, K2 is a lot larger. If I were to tell you, what is 10 plus 1 times 10 to the negative 30th? You would say it'd be 10 point, you have 29 zeros and then a 1, right? So it's not 10, but it's close enough to 10, right? It's just that 10 is so much bigger than that other number, it doesn't really matter. I don't want to go through the effort to plug it in, right? It's an approximation is what it is, knowing this condition. So if I have a sum or subtraction where one thing is way bigger than the other, I can ignore the term that is way smaller, right? It just doesn't make a difference. You actually did something like this in 2A with acids when you were solving for concentrations and stuff like that. And I think you're doing pH calculations and Ka stuff. Or you would say the amount that dissociates is so small that compared to the initial molarity, it doesn't change anything. This is basically the same idea, right? Math-wise. Notice I also say a sum or subtraction because you can't do this with multiplication. If you have a very small term that multiplies something else, you can't just ignore it or say it goes to 0. So the K3 on the top does not disappear, right? This is only for sums and subtractions. So because of this, again, the K3 term we know is going to be much smaller than the K2 term. So I can say that K3, I'm writing this out very explicitly, but I can say K3 times NO plus K2 is about equal to K2. It's close enough, right? And it's because that K2 is so much bigger than K3. And so when I plug this in on the bottom, the K3 NO just goes away. It's an approximation, which honestly seems kind of silly because you have to use the NO on the top anyways and the K3, but I guess here we are. I don't know why you would ever practically do it. And then you get over K2. That's it. You always get the overall rate from the first step. The overall rate will be the thing that you're forming. So typically it's the product in the last step, but then the reactants do come from the first step or from subsequent steps where they kind of get added in and are used for the formation. In this problem, the only things that are used in the beginning are NOBR, NO and BR2. This NOBR, this NOBR2, right, 1 unit, is an intermediate that reacts with NO again. And so you don't have to include it. If there was something else that was not an intermediate, you would want to include that in the overall rate. Any other questions? That was a good question. Okay, I don't see any questions. Any specific questions? So I'm going to, so I'm pulling this from 5 to 7, so I'm gonna have to get off in about 15 minutes. So now would be the time to ask if there's anything specific from a specific test. This one is much the same as the last one, 13. That one's pretty easy. Yeah, I guess we've done one of every type of question. Functional groups, we've done hybridization, we've done pseudo steady state, we've done rates, we've done integrated rate law, we've done overall rates. I think that's pretty much everything. First order reaction. That one we did. Yeah. I don't really know what else to do, since a lot of these are going to be repeats. Like this number 14 is what I just did a second ago. Same thing. You have two products here, but it's still the same idea. You want things only in terms of OF2, and then you write where the O2 forms, you get the concentration of O2F4. And yeah, then you just do the steady state approximation, you solve, and then you substitute. This is the same thing for B. Hmm. Yeah. I'm not sure. Not sure what to do. So I guess I'll wait around for a minute if anyone has any specific questions. Then I may just end it early if there is none. So you guys about a minute. Let's think if there's any other specific questions here you want to do. Have a good one. Okay, so is there an easier way where you can tell if it's first, second, or zero order? For which question? For the pseudo steady state, like if the one we just did, there's no way to tell. There's different ways. So like for number like 13 here, we were told we could figure it out based off of the graph. That's the only way you can do it. If you are looking at an overall rate and you want to know if it's 0th, first, or second order in regards to a reactant, if you change the concentration and it doesn't do anything to the rate at all, it's 0th order. If when you, like, let's say double the concentration, you get double the rate, right? Or if you have it, you get half the rate, that's first order. And then if you, let's say, double the concentration and you get 4 times the rate, then it'd be second order. Or if you were to have it, it'd be 1/4 the rate. Then it would be second order. Zeroth order is the easiest because it's like, well, I change it and nothing happens, right? So I know it's zeroth order. Or first is the next easiest one, right? I double it and the rate doubles. But those are the only ways you can really do it. Any other questions? Just realizing, I don't think anyone from, no, they did, okay. I thought maybe I sent the link to the wrong section. Might have a few people from C17. Okay. So I will stop the recording. Since it doesn't look like there's any more specific questions.